to some company in Japan, because we don't have it we don't have it in Indonesia, so we send them to Kaken in Japan. So based on the result, in average we have like BFA like 91.5, and for the VFE we have like 83.4. I think it's maybe it's good enough for medical mass at that time, because at that time it's very difficult to get the medical mass. Okay, okay, and then I would explain about the membrane for the air for the mass. So the problem with the membrane is like it's used to have a falling. So, I mean, like when some pollens attach and deposited on the membrane port on the membrane surface, it may block and also create some like it growth on the membrane surface, and afterward finally it will like make the membrane become impermeable. And bacteria is one of the microorganism that's cause the problem of the membrane falling here. So our purpose now is why we are trying to decrease the number of bacteria on that grow on the membrane pores. So some people they are already use like a nano silver particle to decrease the number of bacteria growth on the water or also on the membrane. And nanosilver particle, they can like penetrate into the membrane cell, into the bacteria cell, and then kill the bacteria directly. And then we have like a clean water here. In this research, which we are not only use the one single of nanoparticle, we try to use different size of nanoparticle. One is 20 nano, 40 nano, and 90 to 110 nanometer. So we have three different size of nanoparticle here. So how to make the polymer solution? Almost the same way like when we were to make the membrane, the solution for the normal membrane. In this case, we just try to we added like additive like nano silver particles. So we like mixed between the additive and the solvent, and make sure it's completely mixed in the solvent. When we have it completely mixed, and then we add the polymer into this into the case, and then we leave it for maybe around 8 hours at temperature 60 centigrade. And then after like 8 hours we have like a dop solution. And then the same method to use to make the membrane, just by like with phase inversion, just cast into the glass slide, and then control the thickness, and then put in the water bed at a certain temperature. Actually we can also control the pores of the particle by also controlling the water bath. But at this time, we just like a normal water bath, like a 28 centigrade for the water bath. Okay. And then in order to test the membrane whether it's good enough for the membrane for the water or the air filtration purpose, we use like a different type of the test. This what we call here is like a permeation test. Permeation test is including uh, by pushing the nitrogen gas into the dead end cell here. So we have the pressure gauge here, which we set like a 2 bar for the pressure gauge, for the pressure into the dead end cell, and then we place the membrane on the bottom of the cell, and then the nitrogen gas will push the water out of the cell, and then we will have the permeate here. By calculating the volume of the permeation here, we can have like water permeability of the membrane. We have the data logger to monitor real-time monitor for the permeability of the membrane. And then the second one, we did the protein aspiration test. Instead of using the pure water here, we are using protein solution here. So we have like a different type of protein molecule with different size. By that one, we can see the process of the membrane here. And then we calculate the concentration of the protein into the dead cell, and then we calculate the concentration of the protein in the permeate, and then we can compare, and then we can have the rejection of the membrane here. And then for the measurement of the airway process, we can also use the protein solution to measure the protein, the process. And then the last one, we for the antimicrobial activity, we use like river water, any river water. We make sure that the river water is not clean, so many bacteria there. So we just use the river water into the dead end cell, and then filtrate, and then we have the permeate here. and then we check them, and then we take out the membrane here and then put into the uh, coliform agar, and then we grow into the incubator, and then we see how much the bacteria growth on the membrane surface. And also we can also check the water after the filtration process here. Okay, based on the water flux test by using the pure water, we can see that the permeability of the membrane slightly decreased with the introduction of the nanosilver powder, and even getting worse when we have like the bigger the nanoparticle here. It's complete understand that the silver powder, they just like a block on the pores of the membrane surface. And then for the protein aspiration, we can see here that it's not so much different between the pure membrane and normal membrane with the nanoadditive powder here. So we can see that almost the same, and it's like give a similar result. So it's mean like it doesn't really change much the pore size of the membrane. And the rejection of the BSA lies around 91 to 93%. And for the environment, for the process, we can use this based on the what kind of proteins rejected by the membrane. So based on this result, we can calculate the protein that can be rejected, so like a BSA. So it can, so based on this, we can have the pore size is around 69 micrometer. So you can use like you can use like 69 molecular weight cutoff, and then it's the process around 38 Armstrong. It's around 0.038 micrometers. Okay. Okay. And then for the microbial activity, you can see here that also there's some we have like four type of membranes here: the bare PS membrane without any nanoparticle, and then also with the nanoparticle 20 nanomicron, and 40 nanomicron, at the 90 to 2010 nanomicron. So almost all the membrane have like bacteria growth on the surface. But when we use the image to check how much the bacteria appear on the surface, we can see that there's some reduction based on this. So like 70% of bacteria reduce appear on the membrane surface. This is due to that the nanosilver just penetrate into the bacteria cell and then kill the bacteria. But some also, that you can see here, some bacteria also growth on the membrane surface. It can be said that during the filtration process, some nanosilver flush away from the membrane. So that's why there's some bacteria grow on the membrane surface. Okay, so now I will discuss about the water filtration process. So there are many material that can be used for the water filtration system. So some people use chlorine, and some people also use activated carbon zeolite to clean the water. And some people now still using the activated carbon powder in the form of powder. But the problem with the activated carbon powder is that some pollen, some dirt can still pass through between the powder here. That's right. Even though that they have the activated carbon, they have smaller pores that's smaller than the particle or the pollen. But however, some of them they can still pass through in between the particle powder. Therefore, some company they are trying to develop the carbon blocks. When they you have a carbon block, so it will like decrease the chance of the pollen pass through between the powder, because it's completely like attached between powders here. So they have like a carbon block here. It's better in filtration process for the water. The only problem with the carbon block here is it's difficult to make this uh, carbon block. They use like high temperature furnace, and also they use like a high pressure system to make sure that it's completely pressed and then completely compact the block. So this is not it's not cannot be made by like a home industry, also like a small lab. So in our research, we try to make the carbon disc by using very simple method. What we did here is like we mix between the activated carbon powder, we mix with the polyethyl sulfone drop solution, just like a normal membrane solution, and then we mix them, and then we completely mixed, and then after that we just used like a small compaction system, and then we just press this mixture into this, just like this. So we have the mold in the dish form, and then we make sure this, and then we can, and after that we put the dish into the furnace for like 100 centigrade and 100 centigrade for 1 hour. Actually, we can also just put it outside under this outside or outdoor. You don't have to put it in the furnace, but to make sure that this one has a stable for the policy purpose, so we just put it in the furnace to dry the membrane, to make sure that there's no NMP inside the dish. And then once we have this, and then we just put into the water to make sure that to check the bond between the activated carbon powder and the membrane. So when we have this, and then we can start to do the characterization process of the dish. So in this research, we conducted several three type of tests. First, we like a filtration test, total coliform diameter test. For the filtration test, we have this small cell. It's almost same like the cell that we use in the water permeation system, but this one without using nitrogen just to push the water. We just use like a gravity force and make sure that the water will permeate through the dish, and then we have the permeate here, and then we test the permeate, compare the permeate between the permeate and the feed here, and then we can see how much the coliform filter from the dish, also how good is the water is coming from the dish compared to the river, also compared to the water filtered by using the powder. Okay, so we have like for this purpose, we have like a 38% of pH solution compared to the activated carbon powder, 30%, and also 50% of its solution. And then for the coliform test, we collect the water sample from the river. This river used for the irrigation system in Indonesia, in Yogyakarta. So it's completely like very dirty, and there is so many bacteria coliform here. And then we check the amount of bacteria inside the river is like it's about like 24 millions. And then after that we check the water permeated from the activated carbon powder is like a gently decrease. And then we have the good result, I mean the best result from this by when we use like a 38% of the pH solution. So before it's like 24 million, and then now it's the bacteria inside the water after the filtration is only like 1,400. So it's ejected like a 99.9% of the bacteria inside the water. Okay. And then also we also conducted the filtration from the turbidity test, and also by using the metal waste. So we make our own FA solution, and then we check the concentration of Fa in the water, the iron in the water is like a 10, and then after we filtered with by using the activated carbon, this is becoming like a 1. So 1 is I mean it's safe to consume for this water with 1 milligram per liter. And then with the best result we can get like when we use like a 50%, 58% of pH solution into the activated carbon powder. So same, the good results coming from when we test for the turbidity on the river we have like a 14 NTU, and then once we have the activated carbon this we have like 30 NTU. So based on this we can say that the activated carbon this is much better in filtration compared to the activated carbon powder. Okay, so let me explain the reason why it's becoming better, because yes, we can see that when we use the just activated carbon powder, some pollen it can still pass through between the powder. There's a space between the powder. So, but when we use the PS solution, that's amongst between the powder, the feed will not be able to pass through the membrane. So just water coming past through here. So it's better from based on the turbidity, Fa concentration, and also from the coliform. Okay, so we can conclude from this work that we have successfully applied the membrane filter for medical mask by using the non-woven fabrics, this commercial one. And then also we have like 40 nano silver particle that can be used also to reduce the bacterial growth on the membrane surface up to 72%. And also we successfully fabricated the activated carbon disc by using the simple method without using the high equipment and expensive equipment. It can be applicable for like developing country and also like a small lab or maybe also home industry. Okay, that will be all my presentation. Thank you very much for listening. Thank you very much. So I will return the session to Dr. Tuti. Thank you.
Okay, so thank you very much, Dr. Gunawan, for the presentation. It's really interesting to know that one membrane can be useful for many applications for water, for air, for also making a reusable mask that we are really needed that now because the volume of medical waste that is generated through the pandemic is really hugely remarkable, and then we have to reduce that. So thank you again for the presentation. Is there any questions from the participants? If you want to ask, and then you can raise hand on the icon or just type on the chat room. Okay, so meanwhile, before we are waiting for questions from the participants, I have one question about adding the nano silver particles to the membrane, right? So in this research, you have added the nano silver particles for antibacterial and antiviral properties, isn't it?
Yeah. Yeah.
So like from what I know, if we add something into the membrane, then the what do you call it? The water contact angle will be changed because we add something, right, to the membrane. Is it any effect the addition of nanosilver into the membrane for the water contact angle, because this will obviously affect to the water or the air filtration itself, right?
Yeah. Okay, thank you for the question. Yeah, actually, when we added something to the membrane surface on the membrane pores, so they will change the property of the membrane surface. So yes, we also have measured the water contact angle of the membrane when we add the when they have like a silver nanoparticle on the surface, and actually the good membrane is should have like good hydrophilicity compared to hydrophilicity. Because when we have the good hydrophilicity, it's like it's easy to flush away the pollen on the membrane surface. When we added the nano silver particle onto the membrane surface, we can see here that the contact angle is slightly decreased compared to the membrane without any nano silver particle. This is a good sign because when we have this nanosilver and become hydrophilicity membrane, it's going to be easy for us to clean, and then also for the bacteria will not stay on the membrane surface. So it's not it's a good it's a good property for the membrane. Yes, change the membrane porosity, membrane hydrophilicity. Yeah, that's.
Okay. So can I ask another question about this, because this is interesting? So you were doing water filtration and then also for the air filtration, right?
Yeah.
Is there any difference, like choosing what kind of polymer to be used for water, or choosing what kind of additives to be used for the air filtration? Is there any like rules or something that we can follow for deciding which one is which?
Okay, actually, I'm not a membrane guy because some in membrane field, there are some people they used to call used like a membrane guy, because actually membrane is more like from chemical engineering field. Right? I'm from mechanical engineering, so I'm here just trying to use the polymer for this and polymer for that. So actually, yes, based on my experience in membranes, we can there's some type of membrane, some type of polymer is good for the water membrane, some polymer good for the air membranes. It depend on the polymer, also depend on the ratio of the polymer. And actually, when we also some people they the gas membrane is coming from the water membrane. So first they make the good water membrane like ultrafiltration or microfiltration membrane, and then in order to have it used for the gas membrane, they need to like a further modification by some like adding some like a thin film. So by this thin film is more like a diffusion interaction between the molecule that need to be filtered from the air, something like that. So if we want to have the water membrane, we can use like PVDF polymer, polyethyl sulfone, polysulfone, which has like a good hydrophilicity, not hydrophobicity. And if we want to decrease the hydrophilicity of the membrane for the water filtration purpose, we can add some like polyphenol pyrrolidone or polyethylene glycol. Then we can control the porosity, and then we have the good water membrane. And if you want to have like a gas membrane or air filtration for the medical mask, we can also use the same polymer. But we need to make sure that it's very low concentration, and the the coating method also different. So we make sure that it's not properly close the membrane pore. So we make sure that people are still breathing while using the filter media. Yeah, and also if you want to use one the gas membrane, you still need some kind of other purification like a thin film. That's going to be very complicated compared to the water membrane and also for the filter for the mask, medical mask. Yeah.
Okay, thank you very much for the information. So, what I captured from your explanation just now, so in order to make some membrane for different application, uh, we do have like this membrane for this application and the other membrane, the other polymer
Yes.
is for the other application. Okay, thank you very much. Okay, so is there any questions from the participants we in this webinar? Charles, you are mute, I think, I believe.
Yeah. I just want to ask people not to be shy and ask questions. You can type your questions, or if you want to say it out yourself, raise your hands using the icon at the bottom part of this chat room.
Dr. Gunawan,
Yes.
could you please go back to the last slide, the activated carbon one?
Okay.
Yeah, and no, no, yeah, this one.
Okay.
So like from this activated carbon this, what I captured from your presentation is that you want to close the gap, right,
Yes.
between
Yeah.
each grain so that it will be
Mm.
more how do you call it, more compact, and then
Mm.
so the bacteria or the colloids will not will be captured by
Yes.
yeah, by the membrane solution. So in my understanding, this the closing the gaps means it will be sacrificing the filtration, quantity, like the water quantity that can be filtered. Like if I open my tap, I normally have 1 liter for maybe 10 seconds, but because my tap is filtered, I maybe have some 1 liter for 1 minute, like just for the analogy. I think
Yes.
this,
Yes.
yeah,
Mm.
I think this also
Yes.
happens in this activated carbon disk, right?
Yeah. That's true. That's also happening here. So we have three different type of two different type of material here. One is the uh, activated carbon powder, and activated carbon gives the 30% weight of personal polyethylene and 50%. We also run the test like a filtration test, like a feed rate, flow rate of this. Actually, when we do this, and some of the powders actually like hydrophobic. So when we drop the water into the activated carbon powder, the powder one, it's like it's difficult for the water to pass through the powder because it's like a bit smaller, and then like a hydrophobic, it's like a dust, so difficult to go through the powder. Or it also happen when we use the 30% of polyether sulfate. So some of them are still in the powder form because it's not enough polyether sulfate solution to attach them. So it's also difficult. But when we use like a 50% of polyether sulfate, it's give a better flow rates compared to powder, and also compared to this, because of the hydrophobicity of the powder. It's difficult for the water to go to. This is when we use like a gravity force to filter the water. But when we use like a pressure from the water or from the air, I think it's going to be not
Yeah.
so much different between
Yeah.
the
Because
two
there is
materials.
pressure. Yeah.
Yes.
Yeah. Okay, because I think this is interesting because we can have a better filtration result just from a very simple method. And I do believe that because I'm from company, and then I do believe that the chance of mass production is big for this type of activated carbon disk, because it's simple, and then I think it's really simple, but with very good result, I think. Interesting. Is there any question from the floor? So today, Dr. Gunawan is delivering his presentation about membrane that is applicable for several filtration. That's for water, and then that's for air filtration. And the air filtration membrane from this research was used to make a filter for reusable mask. So like during the pandemic, especially on the early stage of the pandemic, like early to 2020 in Indonesia, ourselves, it was really difficult to find medical masks. So people just use cotton fabric mask from cotton fabrics, and then put something inside, filler inside the cotton fabric. So hopefully that will be helping on preventing getting infection. But by time we realized that medical mask contributes really damaging our environment because now everybody in the world is using that, right? So one person can use 2 or 3 medical masks per day, and then that will be contributing to plastic waste, also with other medical waste. So the idea of making reusable masks with filter, that only changing the filter itself, right? It's really excellent because the weight of the filter is really small compared to a full N95 mask or a full medical mask. So yeah.
I think we see raised hands, so we have a questions.
Okay, hi. Can I try to ask some question? I would like to know how long have you developed this project? I mean, you starting when it was COVID, or you starting before COVID?
You are muted, Dr. Gunawan.
Thank you for the question. So actually, we have started this project back like when I was in Kyoto University. our lab is working on the membrane fabrication, but it's used for the gas filtration purpose. And then when I came back to Indonesia, and then we tried to develop the membrane for the water. And then when the COVID came, like when we have the COVID, like maybe 2020, and then we started the develop the membrane for the mask, medical mask. And also just like Dr. Tuti said, Dr. Tuti said that we also have the membrane filter that we use for the as a filter in the cotton fabric mask. So when we have problem getting the medical mask in Indonesia, they try to make the mask from the cotton, uh, like two-layer cotton, and then but it's not two-layer is not enough, so we try to develop a membrane, and then we insert this membrane into between the two-layer, and then we use them as a reusable mask. So it's much cheaper, and we don't really, and the membranes can be used many times, maybe like around 2 weeks, and then once when it's very helpful for the people when they don't have access to the medical mask. Yeah, we started like for the water membrane, we started in 2019 Indonesia, but for the membrane for the air filtration for the COVID, we started when the COVID's in 2020. Yeah.
Thank you so much. It's just because I saw your research compared to Max N95, so and I think it's quite high potential for us to use as a commercial product. So I just want to know more. Is there any chance to have this as a commercial product in the future? And if it is, how long does it take? Thank you.
Yeah. For the commercial one, also we have like we already commercialized it for the membrane, for the mass filter, for the membrane, for the cotton one. But for the reusable one, it's very difficult to commercial because we need to send the prototype to like the US or Japan. It's very expensive. It's cost like maybe 20,000 US dollars. So we haven't started to send it yet. But we Indonesia, we tried some the government in Indonesia. They try to like they try to have like a own laboratory so they can check our membranes and our masks. And also for that's for the medical mask. For this for the activated carbon, we haven't started for the commercials yet, but I think it's possible. But we still need to there's still need something that we need to solve. For example, is it what is the efficient size for the powder, and then the type of the polymer, and then the compaction, and then how much the pressure we need to apply. There's some we need to solve for the problem, and now we are still working on it. So after this one is solved, then I think we are ready for the commercial for this product.
Maybe I can ask something for the N95 reusable mask. So yes, it's true that we already make a prototype of the reusable mask with intention to replace the medical mask and N95 respirator. But apparently, for the use of medical purposes, it has to be approved by NIOSH. There's a certification that is only can be done from by the US certification body. So we have already asked the company that the NIOSH about the certification, and then unfortunately the certification fee and then testing is really huge, and then we don't have yeah, such kind of fund for doing that. But judging from the BFE and VFE, which is 90 and 89%, I think with some more development, the filter can be used for I don't know, like emergency stuffs. But really, we cannot provide for the certification. We can give the value of VFE or BFE, which is required by the medical mask or N95 reusable mask, but we cannot give the certification. So because because the doctors that we contacted, they say you have to have this kind of certification to be able to be used in hospital. So yeah, that is one of the challenges that both the air filtration and the medical mask is facing for the commercialization. So hope that also helps your question. Thank you.
Thank you. So I would like to also know that other than mask that it can apply into, is there any other product that this technology can be applied to?
Yeah, so this mask, this filter is not only for the medical mask also, but we also now developing this filter for the air purifier. So we also fabricated. So I don't explain here, but we also fabricated the air purifier system for like a closed room, and then we already have it, and then we already delivered for the like hospital in Indonesia. So they already use these products. That's so actually the same membrane also can the same membrane for the medical mask also can be used for the air purification system, and but it cannot be used for the water membrane because it's different type of the membrane. Yeah.
Thank you. So thank you. I think that would be all for today. So thank you very much again for Dr. Gunawan and
Thank you.
Dr. Tutik
You're welcome.
for sharing with us today. And thank you very much for all our audience for joining this section. So anyway, if you think of any other question after this webinar, please feel free to send us via the email satu@ncku.edu.tw. So thank you very much. Have a very nice afternoon.